Today's preparation is about power screws. Sorry about the sound quality on this one. We'll be back to normal sound quality soon. What I want you to get out of today's preparation is you should be able to solve for the required torque or the resulting force of a power screw and select a power screw with appropriate properties for a given task. So here are some examples of power screws. You'll find them in car jacks. We've got a screw here going through a nut over here, and so when the screw turns, then the nut advances up the screw and that closes the jack, which makes this part lift upwards. We've got a C-clamp you're all familiar with, and here's a lathe. Whenever you're using the auto feed, this screw is turning and that causes the carriage to move. But first, let's talk a little bit about work, because I think it's important. The book talks about raising and lowering loads with power screws, but I think that it's better to think about it as doing positive or negative work. So work is the dot product of the force vector and the displacement vector, right? You remember that from early mechanics classes. So if we've got a mass here, or any sort of object, it doesn't have to have any mass, there doesn't have to be any gravity. In this case, there is a force of gravity pointing downwards, and we have a force pushing upwards on it. So this is the example of lifting. And when it moves, then the red force is doing positive work because it just moved in the same direction of the force itself. But the blue force is doing negative work because even though the blue force was pushing downwards, the body was moving upwards, and those were opposite directions. That causes the sign to be negative. It causes the dot product to be negative because these vectors are in opposite directions. So positive work is when the force and displacement are in the same direction. Negative work is when they're in opposite directions, and whether it's positive or negative work depends on which force you're talking about. Often we're interested in the force that the power screw is applying to something. And so when it's raising a load like this, the red force might be the power screw, it's doing positive work. When it is lowering a load, it's doing negative work because even though it's pushing upwards, the gravity is pulling it downwards. So this is for the special case of raising and lowering, but let's see how it works in other situations. So we have a spring here, and the spring is already compressed, and our power screw force, F, is pushing upwards on it. It happens to be pushing upwards, but it could be on its side just as well. Gravity has nothing to do with this example. So it turns out that the spring is stronger than our power screw in this case, or the power screw is allowing the spring to expand. When it does that, the force that the power screw is applying to the spring is apparently less than what the spring is applying, and so the spring expands and the force is in the direction that's opposite the displacement vector. So in this case, the red force is doing negative work and the spring does positive work on the red force. Here's an example of a car jack. We've got the screw here and there is a force being applied downwards to it. Now it could be from gravity, it could be from a spring, it could be from anything else. And we could have drawn this horizontal and it really wouldn't matter. When the screw turns, the jack lifts, pushes back against this force. It overpowers this force here. And so in this case, the blue force here has done negative work because it's pointing downwards, but it actually gets moved upwards, and the jack itself is doing positive work. The top of the jack was pushing upwards against whatever was applying this force, and it also moves upwards. The displacement and the force are in the same direction. So the screw here had to have done positive work in order for that to happen. And whatever turned the screw is doing positive work as well. Now, whatever turned the screw, that's applying a torque. It's not applying a force over some linear displacement. Instead, it's applying a torque over some angle. And so here's, we originally were thinking of work as force dotted with displacement, but that is also related to torque multiplied by the angle that torque is applied over. Now, because there could be friction inside the screw, whoever was turning the screw had to do more work in order to cause this displacement to happen to do this work, F dotted with D, up here. Some of that work went into friction, some of that energy went into friction, and whatever's left over went into pushing this force upwards. So in our case, the force dotted with the displacement is going to be less than or equal to the torque multiplied by the angle that it turned over, or the displacement angle. So the actual relationship depends on the efficiency of the screw. The efficiency kind of quantifies how much useful work we got out of it, how much F dot D we get out of the power screw, given the amount of torque and angular displacement that we put into it. Okay, so let's return our attention to screws and calculating the relationships between torques and forces with that in mind. So just as a reminder, this here is the mean diameter of the screw. This is going to be an important parameter. This is the average of the major diameter and the minor diameter. D is the major diameter, D subscript R for root is the minor or root diameter. We also need to know the pitch, which is, as seen from the side, the distance between adjacent threads. Now, actually, in reality, we need to know the lead, which is numerically equal to the pitch for a single start screw. So we're going to be assuming a single start screw and saying that the lead is equal to pitch. And we also are going to need to know the thread angle, alpha. Now, for a square power screw, it's going to be 0. For an Acme screw, it's going to be 14.5 degrees. So let's relate the torque to the force that's being applied by the power screw. So say we have a spring in here, and I'm specifically using a different example than lifting a load because I want to think about positive and negative work as opposed to raising or lowering a load. It's just more general. So if we're compressing this spring, then we are applying with the screw is applying a force to compress the spring, right? If we're turning this in the clockwise direction, righty-tighty, then the clamp is going to clamp down on the spring and it's going to compress the spring. The screw is going to be doing positive work because it is applying a force in the same direction as it is displacing. So there are 3 components of the torque that we need to apply. There's a certain amount of torque that we're going to need in order to do the work of compressing the spring. The torque times the displacement. In this case, the component of the torque we're talking about here, that component of the torque times the angular displacement is equal to this force multiplied by the displacement or the compression of the spring. Right? We're going to have to apply more torque than that because we also have to overcome friction. So there's the torque to do the work, but there's also friction between male and female threads that we have to overcome. And finally, we're going to have the friction at the collar. Now, the collar is basically any other source of friction that we have in our power screw. And in this case, it's the interface between this silvery screw and this pink steel plate, the piece that actually contacts the spring. The screw is going to rotate relative to this pink contact plate, and the pink contact plate will not rotate with respect to the spring. So there's going to be rotation. There's going to be a rotation at this interface between the silver gray and the pink. So there's going to be friction there as well. So it's not just between the male and the female threads. There's also going to be friction here that we have to overcome. So a certain amount of torque is required to do the work. We also have 2 components of friction that we need to consider. So the first 2 components, the torque required to do the work and the friction between the male and female threads, is given by this equation here. And this is the equation for raising a load, right? The TR is for raise, but that's the same as doing positive work. That's the same as if we were pushing down on the spring. The force that the screw is applying is in the same direction as the displacement, positive work. And here we have the force that we're applying, the mean diameter of the screw, the average of the major and minor diameters of the screw. We've got the friction coefficient of the threads. We're talking about between the male and the female threads, how much. We also have the thread angle. So again, for a square threads, it's going to be 0. For an Acme thread, it's going to be 14.5. And finally, we have the lead. So if we have all those parameters, we can plug and chug and we can find out how much torque is required to apply that much force, whatever force we need. Or we could turn this around, right? We could figure out how much force we can apply with a given torque. If we were letting the spring decompress, if this interface were moving upwards and the spring was expanding, then the force that we are applying on the spring is in a direction that's opposite the displacement. And so this is the same as, say, lowering a load. We're doing negative work here. And we've got all the same variables. The only thing that's changed about our equation is that there's a sign change in two places. In order to solve problems that are involving torques and forces in power screws, these are the equations to use. Their source, you can take a look at the derivations in the other videos I provided. It basically boils down to thinking of the screw threads as a ramp, and so you just unwind the helix, and the analysis is it's surprisingly straightforward for maybe as complicated as the equation looks. So that's the first two components, right? This was the torque that was required to do whatever work that is being done. You need to put in a certain amount of energy, and you're displacing a certain amount, theta. You need some torque over that angular displacement, plus whatever friction there is between the male and female threads. We've got to overcome that. Now there's a second component, or a third component, excuse me, a second component to the friction, and it's the friction at the collar that we talked about. Basically any other friction in the column. For all power screws, there's usually some other place that there is going to be friction, because the power screws are always going to contact the thread somewhere, and they're always going to contact something else. In this case, if you are clamping down on a part, you often don't want this pink thing to rotate with respect to the part. So there's going to be some rotation between the screw form and this pink part here, and we call that the collar. And this friction, we usually just model it as though they're a force, a friction force that's being applied at a radius. So that's where this equation here comes from. Tc is the torque from the collar friction. Here's the friction force that's being applied at some radius. So if this collar had a diameter, let's see, between say here and here of 1 inch, then we'd probably use that as the diameter. That would be conservative. In reality, there's sliding going on everywhere from the center to the very outside, and there's really a pressure acting over that. But just to be conservative, we pretend that any of that friction force between those two parts is being applied at the maximum radius. So we usually take the collar radius to be the maximum, just for simplicity of analysis and to be conservative. You can use your judgment on that. So let's do an example here. So here we have a simple jack screw. All right, so here is the base of the jack screw in red. The screw itself is white, and we're going to turn this handle on it. We're going to rotate it so like this end, if we wanted to rotate this thing clockwise or righty-tighty as viewed from above, then we would pull this end towards us out of the page, and this end we'd push inwards into the page. And then on the top here is kind of like there's a collar interface, and this purple part, we don't want it to rotate with respect to the load. So this purple part of the jack screw, or the screw jack, is going to be rotating with respect to our screw piece. So I've put in different colors the things that rotate with respect to each other. All of this white is one piece. This red is one piece that's separate from the white. There is going to be relative movement between the red and the white here, the female and the male threads. And likewise at this collar interface, we're going to have sliding between the purple and the white. What we need to know is how much torque is going to be required to raise the load, how much torque is going to be required to lower the load. I could have also asked if I wanted to, if I had a certain amount of torque available, what amount of load could I raise? Or what amount of load could I lower? Because you think, oh, it should be easy to lower the load. Yeah, but there's friction to be overcome. So you have to have enough torque to overcome that friction at least, even though you're not doing any positive work, even though the load is actually helping you out. That's how I usually think about it, right? I don't think about it in terms of raising the load or lowering the load. I sometimes don't even think about it in terms of doing positive work or doing negative work. I say, all right, if the thing that I'm pushing against, if that is impeding my motion of the screw, then the screw must be doing positive work. That's kind of the TR, the raising the load equation. If the force is helping me turn the screw, then I think of that as lowering the load, or the negative work, the TL sort of equation. So the numerical values of the parameters here, we've got D sub 1, the diameter of the screw is 1.5 inches. We've got D sub 2, that is the diameter that we're going to use for the collar interface. That is going to be 2.5 inches. And so let's say that, yeah, this is 2.5 inches, even though actually everywhere here there is some amount of sliding going on. We're going to assume that the purple and the white just contact at the very outer diameter. And so whatever force is between them, whatever normal force is required to support this load, it's at the maximum radius it's going to require more torque. And that is conservative for our problem. We're going to overestimate the amount of torque that we need. Now, sometimes you might want to turn that around, so you need to decide for your problem whether you want to use the maximum radius or the minimum radius and somewhere in between. Again, that's a matter of judgment. We have a mu between the threads, the male and female threads, of 0.08, and mu c is equal to 0.1. That is the collar friction. Let's go ahead and call D2. We'll call that DC. DC for the diameter of the collar. And that'll allow us to call this just D instead of D1. We also know that this is an Acme thread, so that means that alpha is equal to 14.5 degrees. And it's got 8 teeth per inch. Now, what is that useful for? Well, ultimately we're gonna need the lead, right? So teeth per inch is the inverse of the pitch. So 1 over P is equal to 8 teeth per inch. Teeth is not a real unit, so it's really 8 over inches. So the pitch is 1/8 of an inch. And that means that the lead is 1/8 of an inch. So our equation for raising the load, force here, times the mean diameter, which we'll calculate in a second, over 2, multiplied by L, the lead, which we just found out, plus pi. Mu here, mu is the between the two threads. We've got the mean diameter showing up again. We've got the secant of alpha, which is 14.5 degrees in our case. And this is all over pi times the mean diameter minus mu L sec alpha. That's going to be the torque that's required to raise the load. But you know what? That's only going to get us as far as accounting for doing the work to raise the load and overcoming the friction between the threads. We haven't considered the friction of the collar yet. We're also going to have some collar friction. So we're also going to have to figure out collar friction, which is going to be the force multiplied by mu, our coefficient of friction for the collar. So mu at the collar times the force times the radius that acts over, which is the collar diameter divided by 2. Let's figure out this d sub m. So dm is equal to the mean of d and dr, so outer major diameter and minor diameter divided by 2. The relationship between the major diameter and the minor diameter is that for power screws, the thread height is the pitch divided by 2. And so the difference between the major and minor diameters is the pitch. So d sub r is d minus the pitch. So this is 2d minus the pitch over 2. And let's calculate it for our example. We've got 2 times 1.5 minus the pitch of 1/8 of an inch divided by 2, 1.4375. And you should check yourself there. It should not be too much smaller than the outer diameter. So this makes sense. It's a little bit smaller than the major diameter. So I think that we can plug and chug on this TR here. So let's go ahead and do that. Should probably give a value for the load. F here is equal to 4,000 pounds. We'll need that. So let's do that. 4,000. I'm not going to write out d sub m. It's given there. Mu, again, we're going to be using the mu for the thread interface. Secant is 1 over the cosine, so maybe that's how I'll write it. Or actually, let's go ahead and calculate it since it appears in 2 places. Secant of alpha is 1 over cosine of alpha, 1 over cosine of 14.5 degrees. Make sure you convert from degrees to radians if your calculator needs it. That's 1.0329. Notice that this is going to be increasing the amount of friction, right? This gets multiplied by the friction coefficient. So for an alpha is equal to 14.5 degrees or 1 over cosine. Cosine is not too much smaller than 1, so this is only a little bit bigger than 1. It only increases the friction a little bit. Square threads, then cosine of 0 degrees, alpha is going to be 0 degrees. It's going to be 1 over 1. This will just be 1. it doesn't increase the friction anymore. So the greater your alpha angle, your thread angle, the more friction you're going to end up having. You can see that you would have more for the 30-degree thread angle that you have for fastener screws. That's why they use shallower thread angles for power screws to have less friction. So in place of secant alpha, I'll just put 1.03 and over many of the same things. And we have 317.87 inch-pounds force. All right, let's evaluate this one. Mu for the collar is 0.1 times our force, 4,000 pounds. So the friction force at the sliding interface, right? Let's view the sliding interface. We're viewing this from the top, and so we've got the purple part is touching this white part here on the outside, and it's applying forces that oppose the rotation. I think we'd actually be rotating, trying to rotate in this direction. Then the purple is going to be opposing that. It's going to be pushing downwards, and there's going to be a friction force that's opposing that here. And we're pretending that it occurs at whatever the full radius is, right? We'd have a smaller torque if it were acting somewhere in between, or if it were actually, in reality, it's a pressure that's over this entire area. And so it's some integral of the pressure, something like T is equal to the integral of mu times the pressure times the radius we're at times the little amount of area. So over the entire surface, something like that. But we've just simplified it. We're saying it's going to require more torque due to friction. We're going to calculate a upper bound on the torque required to raise the load if our numbers are right. So the diameter of the collar is 2.5 inches divided by 2 becomes the radius. So we actually have more friction coming from the collar than from the threads themselves. So sometimes to reduce friction in power screws, they put kind of ball bearings at the collar interface, thrust ball bearings, and they'll have maybe even balls inside the screw here so that there's rolling instead of a sliding action. We're not going to analyze that separately. Suppose you could just think of that as just a low coefficient of friction. Okay, so the total force required to raise the load is T is equal to TR plus TC is equal to 317.87 plus 500, and we have 817.61 inch-pounds. It's almost the same calculation for lowering the load. T equals TL plus TC, so we're going to have the same TC before because it doesn't really matter which direction this is rotating. We're still going to have the same friction torque required here, but we're going to have some sign changes for lowering the load. Now actually, the form of the equation that I wrote up here, you need to be careful about what form you write the equation in. The way that it's written in the book puts the L up front here, plus pi f dm, have a minus L here, and on the bottom it was pi dm minus FL. F is the same as my mu. It becomes a plus sign. So you need to be a little bit careful. The way that I've written, I think, is a little bit more convenient because you just flip these signs. Here, it didn't just flip the signs. It put a minus in front of this L, and it flipped this sign. That's a little different from how I've written it. This here is still a plus. This up here is a minus. And I get 157.629 inch-pounds. Now, if I had messed this up, if I had made this a positive and made this a negative, then this whole thing would end up as negative 157.629. So it's not such a big deal. Just know that if you get a negative number, you probably mixed something up with the signs there. So even though I wrote this probably backwards, I probably should have. Here, let's correct this right now. We'll write it more closely to how I did in the presentation. In the presentation, it looked like. And so down here, now in this form, we can just simply change both of these signs. This will be a minus, that'll be a plus. You run that out, you'll get the positive, this answer. So that's why I wrote it like this in the presentation. It's just a little bit simpler to remember that you change the signs, both the top and the bottom. Okay, So let's talk just a little bit about efficiency. I would not just blindly apply the equation in the book. In Shigley, it gives this equation for the efficiency, and it puts TR down there. And you need to think about it. Is TR the full torque that's required to raise the load or to do the positive work? To do whatever you're trying to do with the screw? No, you also need to consider the collar friction. So I wouldn't use this. I would go back to the kind of the definition of what efficiency is. It's the useful work that you were able to accomplish over the energy that you put into the system. So in our case, that's the ideal torque times the displacement, the angular displacement, which is basically the no friction version. If we didn't have those two sources of friction, all we were left with was the actual work that we were trying to do. So the ideal torque with no friction multiplied by the angular displacement over the energy input. The energy input is the actual torque we have to apply multiplied by the angular displacement. So let's figure out what the ideal torque is. What is the torque that's required when there is no friction? So if you take our equation and you plug in mu is equal to 0 on both the top and the bottom, you'll find that it simplifies down to FL over 2 pi, which does appear in the book. So the book calls this T naught. So when this simplifies to ideal torque over actual torque, our efficiency is T naught over not just TR, but TR plus whatever the collar friction, or whatever total torque that you actually have to apply. So in our case, what is T naught? T naught is FL over 2 pi, is 4,000 times the pitch of 1/8 inch over 2 pi. So if there weren't any friction, it would actually only take 79.58 inch-pounds in order to turn this thing. See, even when we're trying to lower it, there is almost double the amount of torque that's required because of all the friction. And when we're trying to raise it, it's way, way more. Now, maybe I should have finished the lowering calculation if we want to add these two together. Oh yeah, so the torque required to lower the load, considering the collar torque, is pretty substantial and way more than the ideal torque. But we're calculating the efficiency of raising the load. It only ever makes sense to calculate the efficiency of raising the load or doing positive work, because the efficiency of doing negative work is really, really bad, right? It shouldn't take any energy in order to do negative work. You can do negative work with brakes on your car. So it only really makes sense to calculate the efficiency for raising the load or doing positive work. We've got the efficiency is equal to T naught over the torque for raising, which is TR plus TC. That is 0.0973, which is about 9.73% efficiency. Very low efficiency on these things because of the friction. Even though the coefficient of friction were pretty low, you've got low efficiency. Now you can make it a little bit more efficient by going to a square screw because there's less of thread angle, and so that secant alpha doesn't hurt you as much. But in general, power screws, unless they're ball screws, are pretty inefficient. Now as you're going through this, be careful. You need to really think about what the full torque required to raise the load is. Notice how I didn't figure out a new letter to use here. I used letter T in both cases for raising and lowering. And because the book has already taken up the symbol T subscript R and T subscript L in order for just the part that's independent of the collar friction. You always need to remember to add that collar friction in there to get the total. So be careful about that when you're solving your problems.